Hello, this is Greg Allison with Galactic Greg's coming to you from an undisclosed location somewhere in the Milky Way galaxy. This video is a presentation by a gentleman by the name of Dr. Jonathan Witter of BWX Technologies Incorporated about nuclear thermal propulsion and why this could be very important to get men and women to the planet Mars, why it can save time, and many of the advantages about it, the history of nuclear thermal propulsion, and there's some discussion, especially in the Q&A session with the audience, about other forms of nuclear type fusion propulsion. This is a presentation to the Huntsville, Alabama L5 Society. And please, I have many more videos coming up about this and so many other topics. If you've not already subscribed to my channel, click subscribe and bang the update notification bell and support this channel. I've got some links below that I also share with my sister channel, Green Greg's. So I hope you enjoy the video.
Hello, I'm Greg Allison. I am president of the Huntsville, Alabama L5 Society. We're the local chapter of the National Space Society, and our objective is to see people living and working in space on a permanent basis. Basically, space colonization, as some people call it, or space settlement. That's our long-term objective. Of course, we've got a lot of steps to take to get there in terms of space exploration and development. But that's our ultimate goal as a society. And HAL5 has been here in town since 1983. We started, actually, Conrad Dannenberg called the first meeting. I was the founding president back in the day. Spent a few years in that job and have recently returned to it. And we have, in this chapter, done a lot of things. We have monthly programs to outreach to the public to be informative about what is going on in space, what some of the potentials are. We've had a history of doing some conferences, some International Space Development Conferences in 1993 and 2011. And we did a program of developing hybrid rockets. We launched some altitude balloons. And we made the Guinness Book of World Records from our launches, and there have been a lot of spin-offs from those activities. So we actually are still continuing some of that program. We called it Halo. We do some rocket workshops up in Gurley, and we have a lot of other activities. Our next program is going to be September the 12th here in the library, and our speaker is going to be a speaker from our recent Apollo panel. I'm getting Luke Talley's his name. Yeah, Luke Talley's our next speaker. He worked on the inertia ring, the instrument unit for the Saturn V. He's one of the founding guys of digital electronics, and very interesting guy, a lot of good background. And we're going to have some more of these Apollo engineering veterans to talk to us over the next few months and years while we're celebrating the 50th anniversary of these Apollo moon missions. And I'm wearing a cap for that tonight in celebration of that. And also to keep my hair out of my face, it helps, you know. So yeah, our membership requirements are real stringent. You just have to be interested in space. If you're interested in it, you got a welcome home here. That's what our club's all about. A lot of things in HAL5, we try to be an interesting group and do a mix of things. We're involved and engaged in the community. All that said, that's enough stuff up front here. So tonight we've got a real good, interesting technology discussion about nuclear propulsion in terms of deep space travel. It's suggested it's the way to go to get us to Mars a lot faster. So we'd like to hear what that means for us. So our speaker tonight is Dr. Jonathan Witter. He's with BWX Technologies. He is the chief engineer for their programs and their advanced technology program. So ladies and gentlemen, I give you Dr. Jonathan Witter.
Thank you for inviting me to come talk a little bit about nuclear thermal propulsion or nuclear rockets for space exploration. I am the chief engineer at BWX. I'm currently working on with our contract with NASA underneath the game-changing development organization for looking into the feasibility and concept development for a nuclear rocket engine with some specific key performance parameters that they wanted to look into. And we'll get into some of those attributes that they're looking for currently versus what they were doing back in the 60s with the NERVA program. So I've got one quick video that's there that is their promotional video from NASA. And I'll make sure that hopefully I get the speakers turned up high enough. It may be a little bit hard to hear, but if not, you can just search game-changing development, nuclear thermal rockets or thermal propulsion, and this real short video will pop up. There's no sound yet, but. If you can't hear it, I'll try to explain what's going on in the video, or I'll talk more about it in parts of my talk. But I borrowed some of the imagery from this. Yeah, you probably can't.
First generation nuclear thermal propulsion, or NTP, could enable both faster transit between the Earth and Mars and a series of advanced space missions. Nuclear thermal propulsion is powered by nuclear fission.
So we'll talk a little bit about that.
For more than 70 years.
It would make it loud.
How it works.
I can't make it that loud, I'm sorry. So they're talking about the process. So nuclear fission's used, talking about heating up the hydrogen propellant through the reactor engine. I've got some other images of that. The efficiency of the thrust, or the ISP, being higher than a chemical rocket. So they're doing a comparison of chemical rockets.
Was considered for use in the Apollo program.
During the Apollo program, so celebrating the 50th part of that, they also had a parallel program going on with all sorts of space power and space propulsion, the SNAP reactors and the NERVA rover program. And this shows some of the testing that they were doing out in Nevada. Challenge then, they were using high enriched uranium versus low enriched uranium, which is more politically acceptable these days. But there's a challenge using low enriched. We'll talk a little bit about that. Also, before they're able to do tests, we'll see some images that they used to just test the engines out in the middle of the desert in Nevada. Today we can't do that, so we have to have some sort of capture system. So we're looking into capture systems for capturing the exhaust. And we'll talk a little bit about what that kind of means. And we're taking advantage of E equals mc squared. That there's high energy content in the fissioning of uranium, such that you don't need an awful lot of mass or fuel to provide the heat, and it allows you to have lower hydrogen tankage to do it, and then be able to get to deep space exploration more rapidly because you've got higher efficiency thrust. And now they're showing some other parts of the current NASA program also looking at kilopower systems. And so this is showing a little grid farm of some kilopower systems, which they did do a test last summer in Nevada, again on a small kilopower scale power system, which was a very successful test at Los Alamos, that test site in NASA Glenn, working now. So look for this on YouTube, and then you'll be able to hear it. All right. Okay. So back to there's another. You can go back to some old videos where there was a NERVA promotional video. It was like a half-hour video about the whole NERVA program. They had all sorts of great cartoons. It was probably about the time frame that Werner von Braun was working with Disney, because they created these great cartoon movies of the technology. And then it has some nice things to kind of explain the fission process and mission profiles that they're looking at doing. So it's another. There are a bunch of old movies online that you can find. Whoops. Oh darn it! I don't want to do that. Skip that. Okay. So one of the goals of the program. So Glenn Seaborg was the chairman of the Atomic Energy Commission. The NERVA program was a joint mission joint project between the Atomic Energy Commission, which is what the Department of Energy is now, and NASA. And so there was a Space Nuclear Propulsion Office set up at NASA Glenn, and what they were saying they wanted to do is what we're attempting to make is a flyable compact reactor, not much bigger than an office desk, and literally they're about this big, that will produce the power of Hoover Dam from a cold start in a matter of minutes. And so this image here is a test, one of the tests, that was a 4,000 megawatt thermal reactor. That's enough to power that's bigger than a commercial power plant, megawatt rating. So they tested that, and they ran it for a while. That was one of their biggest tests. It was a 250,000 pound thrust engine that they were testing. The dewars there are 500,000 gallon liquid hydrogen dewars set up in the middle of a hot desert in Nevada. And so the technology that they're doing to build these test facilities and test a number of rockets, essentially 2 a year they were testing out of Nevada, and we'll see that. But essentially what they're trying to do is they needed to be able to start it up fast and produce the power of Hoover Dam in the size of essentially a little bit bigger than a desk. I used to say trash can, but I don't like to say that anymore. People misquote me when I say trash can. So what are the fundamentals of nuclear thermal propulsion? As we saw in the video there, the cartoon shows kind of like a hot reactor system. Essentially, the reactor serves as the combustor, except for we're not combusting anything. We're just providing heat to heat up the hydrogen coming from the propellant tank and pumped through the system and then pushed out the back end for the propulsion. So we heat the propellant by a nuclear reactor. All the nuclear reactor does is provide heat. And then essentially the hydrogen is the coolant to the fuel. The nuclear engineers think of the coolant, the hydrogen as a coolant. The rocket people think of it as the propellant or the fuel. So we heat it up and we need to cool that fuel so it doesn't melt. So you can have the engine thrust long enough and also to be able to reuse it because you got to turn it on again to stop where you want to go. We can use we typically use the lowest molecular weight. We can use monopropellant. We don't have to have 2 different tanks of oxygen and hydrogen or whatever. We just push hydrogen through there because we're not combusting it, we're just heating it. And so having low molecular weight is key for having good ISP. So our molecular weight is 2, or if we dissociate it, get hot enough to dissociate it, we can get a molecular weight of 1. That's the best you can ever do with a gas coming out the back end of an engine. So that gives us the possibility of having 2 times the ISP of a chemical rocket, which are limited by you're pumping out steam. So the lowest molecular weight you can get to is maybe hydrogen-rich steam, so maybe your molecular weight's about 11. You're at a hotter temperature because you may be up at 3,500 Kelvin or something, but you've got that molecular weight that kills you. So that's where nuclear rockets can get double the ISP than a chemical rocket. And we're at a lower chamber temperature to do that. What we nuclear engineers care about is, well, what's the thermal power of the reactor? Do we need 4,000 megawatts or do we need a lower amount of power? And then that's what we have to cool within the reactor system and provide enough volume and power for the power density to be cooled. So for about a 25,000 pound engine, we need about 500 megawatts. That's still an awful lot of heat when you think about it. And that can give us an ISP of about 900 if we come out with those chamber temperatures close to, I guess, some 4,600 Rankine, 2,500 Kelvin. I'm having to live in a world of British units, metric units. It's a little bit weird. So a lot of my slides, I like PSI, but I like Kelvin. So it's a little bit of a mishmash of units. And I like pounds thrust, not kilonewtons, because what the hell's a kilonewton? So the amount of fission, amount of uranium that we need to fission, though, this is where E equals MC squared comes into play, is that to go back and forth to Mars with 3 of these rocket engines that are 25,000 pound engines, we're only burning the core for about a half hour to an hour total. And in that time frame, 500 megawatts times 3,600 seconds, 1 gram per megawatt day of fission, uranium fission, we only use about 100 grams of U-235 to go back and forth to Mars. Now we need 120 metric tons of hydrogen to do that, but we only need 100 grams of uranium to do that, and that really could be the size of, I usually try to bring a sugar cube, it's about the size of a sugar cube if you have that amount of uranium that you fission. Now that's all in this big reactor, but you need a heck of a lot more fuel in the system, the uranium, to make the reactor critical and be able to operate hot. But the amount of stuff that we actually use in fission is only about 100 grams. So that's the beauty of nuclear power as well, is that you get high energy density for your heat source. So people, sometimes NASA likes to say or this, or the newspapers like to say this, where, oh, we've got nuclear power for Cassini, we've got nuclear power for different things, the Mars rovers. That's really radioisotopic thermal generators, or general purpose heat sources. And all that is plutonium-238 that decays with its radioactive decay, it emits helium or alpha particle or helium atom, and that gives off a lot of energy. It gives off like 5 MeVs of energy. So it's a lot of energy, high energy density. It's a big particle that has to slow down, and that gives that kinetic energy transferred into thermal energy. The beauty about 238, even though people don't like using plutonium because it's really hard to work with, is that it's got an 88-year half-life. What that means is, after 88 years, I start off with 100 grams of plutonium-238, emitting all this heat. In 88 years, I have 50 grams. And this is why the deep space missions can last 18, 20 years with power supply, because they have the heat available to do it. Where solar panels, you've got to go deeper and deeper into space, you get less and less solar emittance to the solar panels. This is a constant heat source, essentially, for 88 years, which is the beauty of it. They've looked for other radioisotopic generator sources, like strontium or other things, but they all have a lot shorter half-life. And so if you have a long mission that lasts 20 years, like Cassini just did, you would say, well, gosh, I need to put more and more material in there, and my decay rate of my heat source in, say, 10 years is half. And so now I've got, how do you manage that decay of your heat source, which is a decay of the power of the system? So that's where radioisotopic generators, they've come back to saying, you know what, plutonium-238 is really the best. Let's figure out how to produce more of it. It's really expensive to do it, but the Department of Energy is looking into ways to do it, because we don't really have plutonium production reactors anymore because of the weapons reductions. So they have to find different ways of getting that plutonium, or have the stewardship of the available material that they have in hand. Fission, on the other hand, you're fissioning U-235, and essentially a neutron will come in and it will split the atom in half, and you'll get 2 to 3 fission products. But they're zipping around at really high energy. Now we're up at 190 MeV coming out between the two, and that energy, those big particles stop very rapidly in the solid material, give that kinetic energy, turn it into thermal energy. Then that thermal energy needs to be transported to the gas. And that's the trick of getting that heat out into your coolant or into the propellant. And the process then also gives off a couple more neutrons. So for every 1 neutron that comes in and fissions, we get about 2.5 neutrons that go zipping around. We just need 1 more of those neutrons to come back into another fission atom to keep the system self-critical. Or critically, you hear about critical reactors or self-sustaining chain reaction, is that I've got 1 neutron come in, I got 2.5 come out, I got 1 more to come back in to keep the balance 1 for 1, 1 for 1. What that means is that 1.5 neutrons can go wherever the heck they want, as long as I get 1 more neutron coming back into fission again. And then the power level is just the rate at which that fission happens. So reactors are called critical if the reactivity is 0, or if the neutron balance is 1 and 1. The rate at which that happens is the power level, and sets the flux level. So that's the fundamentals of nuclear fissions, and how now people, what do you do with it? We've been using it for 70 years in the United States. We did actually build 1 space power reactor, the SNAP-10 reactor, and flew it back in the 60s. But then the Russians have flown 30 some odd reactors, and they're still up there. Well, 1 came back into Canada, but the rest of them are up in space. Yeah, it was the Rorset that came back in, and there was a big race to get it and things. So there's some online documents about that. And so that's essentially what we do, is we're going to use this fission heat to heat the propellant. Okay, so why? We already talked a little bit about the ISP. Bill Emmerich at Marshall Space Center, he's got this great book that has an interactive PDF associated with it, and you can play with the figures. And at first I don't really like electronic learning, but playing with this book and playing with the figures, you can just use the slide bars for a bunch of the figures and the equations that's in there. And you can get a real feel for what's really happening with the equations in the book. And so I did that with the ISP. I picked a propellant for hydrogen-rich steam, essentially, with a molecular weight of 11, and came up with, okay, there's the ISP of 450. And then I did the same thing for just hydrogen. And so now we're at like 2700 Kelvin, getting 900 seconds of IP. So lower chamber temperatures, higher ISP. But that book's a great book for the fundamentals of nuclear stuff and also the nuclear thermal propulsion. And you can play with the figures pretty nicely. It doesn't show up all that well on the screen for what's going on. So I have a couple different images of the system. This is an image of one of the Nerva rocket engines, and I think they're two different. They can have different engine cycles. So one, you can be a bleed cycle, take some hot gas off of the chamber, and run the turbo machinery, and then port that overboard. That's what most of the Nerva test engines were a bleed cycle. You bleed off some chamber gas and have it hot, mix a little bit of cold gas with it so you can go to the turbine and spin the turbine and run the turbo pumps. In an expander cycle or a closed topping cycle, you take some heat from the regen section of the nozzle, so the flow would come to the nozzle, cool the parts of the section of the nozzle that need to be cooled, have flow come up through the ready reflector, and we'll see a different picture of what that means. We need a reflector to reflect some of those neutrons back into the core because we can't lose more than 1.5 of them. So we bounce them back in with a rated reflector. That bouncing back in is heat transfer as well, so that beryllium reflector needs to be cooled. So it picks up some heat. Then if we have moderators in the core or not, that heat then is the heat that's used to drive the turbo machinery, and then it pushes all the flow into the reactor where the most heat happens. So we'll go from cryogenic temperatures from the propellant tank, like 27 Kelvin, push it through, come out of the reflector maybe at 250 Kelvin or 300 Kelvin, or actually a little bit hotter. Then we come out of the turbine and we may enter it into the reactor at about room temperature gas. And then it heats it up across a meter to 2700 Kelvin. So a temperature ratio rise of 2500 Kelvin across a meter. So there's a lot of energy being pumped into the gas, which means that you're running on the dicey edge of how hot the fuel is, and if anything happens to that flow, well, the fuel's going to melt. And that happened a couple times in some of the Nerva engines, where one time they had a pressure sensor that went bad. They thought they had flow, but they didn't, and they melted half the core. But 6 months later, they were testing on the same test stand. They were able to go in there, clean it up because low fission product inventory, because they weren't really burning it all that long. So with testing, things happen, and that's why future testing would need to be done with more care and less cavalier approaches, and also being able to capture any sorts of melting of the fuel through a capture system. So real simply, I already kind of talked about this. This kind of shows a simple flow path. This is what we show to the management level when we're talking about nuclear thermal propulsion. But it's really kind of key to, in the past, people just thought about, well, let's just focus on the fuel, let's just focus on the engine. But it's really a very, very tightly coupled system, especially with an expander cycle, when you need that heat energy from other parts of the reactor to feed the energy source to drive the turbo pumps. And so this is where we really need to be interacting with the engine side of it and the reactor side. Each one of the groups need to understand what's happening with the flow, the pressure drops, the pressure fields, the temperature differentials. And that's what we're up to now, is working closely with the engine folks to make sure they understand the intricacies of the reactor inside that reactor vessel. It's not just a combustor where I'm just pushing fluids together and letting them burn. We actually have to manage the flow paths, manage the flow fields, and manage the heat transport. So there's a lot more heat transport associated with it than just combusting the two gases. And so, like I said, it picks up some heat. Probably about 3 to 5% of the heat isn't deposited within the fuel. And so that gives you a couple megawatts to use to drive your turbo pump. So there's plenty of power to run the turbo pumps in an expander cycle when you take that heat from those regions. So all the parts of it, all these other parts now, if we're doing a cross-section of what one of these NTP engines look like, you have the center region, which is the core, or the fuel area, and that may be a mixture of fuel and moderator, or it may just be fuel and fuel elements, which would have cooling holes, passages to let the gas flow through that solid, kind of like a big heat exchanger. Essentially, the core is just a big heat exchanger. and the heat is internally produced within that heat exchanger. The edge of it has the radial reflector, which is what I was talking about, that beryllium reflector. Sometimes they might use aluminum or other things, but beryllium's got some nice properties that it actually takes one neutron in and sometimes gives you 2 neutrons back. So it's a little bit of a booster for your neutron economy. The circles in that radial region are control drums. So we need to control the reactivity. So we need to be able to shut the reactor down or turn it on. And the control drums are just move poison that are located on arcs. And the drums would just rotate the poison out, in and out, to control, essentially we use that to control temperature. So as the reactor heats up, it adds negative reactivity or negative neutron balance. And so we have to rotate the drums out to rebalance the neutron population. So neutrons that were going to parasitic loss in the fuel, we rotate the poison out and allow more neutrons to reflect back in. So we trade neutrons being absorbed in the fuel for neutrons being absorbed not in the poisons. And so we can control temperature and power level with that, maneuver the engine. All the other parts are all parts of the engine. So the nozzle, the chamber, the propellant feed lines, or the propellant being the liquid hydrogen, and all the other piece parts, all the subcomponents. And NERVA days, they would have been testing all those subcomponents in separate tests and then joining them together. Most of the NERVA tests were just breadboard tests where they just fed the hydrogen to the reactor. So they were more reactor tests than engine tests. The last set of testing was the XE Prime, where they actually integrated the engine system with the reactor system, because they were reaching that stage of developing the TRL levels of the engines to the point where now they can finally mate the engine system with the reactor system and do the full startups with that. So that the evolutions of the program were building up to full flight systems. Zooming into the fuel, you can see that they made a bunch of little hexagonal pieces. In this case, it was a graphite-based, carbon-based ceramic material. And they started off with just having these little BBs of uranium carbide or uranium oxide coated, and then they just mixed it into this graphite matrix and formed the fuel elements. If you read some of the old reports, they actually used a commercial meat grinder, and they had a picture of the commercial meat grinder. To make the fuel, they would push it through what I call a Play-Doh machine and extrude the elements to be about 1 meter long, and with a die set so you could get the 19 cooling holes into it. And then they would check it and say, well, the fuel isn't mixed in there well enough, so threw it back into the commercial meat grinder, grind it up. They did that 3 times to get the particles well distributed through the entire length of the article. And so sometimes you don't need fancy machines, you just use what's commercially available, and you can make some stuff. They had limitations on with the temperature capabilities and the some thermal stress mismatches and stuff. So their early fuel elements had a lot of problems. And so the evolution then went to more of a solid solution where they mixed the uranium into the graphite mixture and maybe with some zirconium carbide to have higher temperature capability, and came up with a composite matrix in the end. At the end of the 10-year effort, they came through with, at the end point of using a graphite-based system, to a composite matrix. And so they got well-blended fuel, put coatings on it to protect that material, because hydrogen likes to eat oxygen and it likes to eat graphite. And so they protected it with a niobium carbide coating or zirc carbide coating, because niobium is more of a neutron poison than zirconium. They would make that arrangements in there. They would cluster the cluster assembly on the left-hand side. They would have a center tie tube, which could either have graphite basis, or later engines ended up putting into those circles zirconium hydride moderators. So hydrogen moderates, slows down neutrons, make the neutrons really, really nice for the U-235. So the later elements, they would put 6 fuel elements around a center moderator tie tube element, and they would have that tie tube attached into the core support plate, and they would kind of screw everything together into this unit cell of 6 fuel elements and 1 moderator tie tube, and assemble it like a puzzle into that encircling diameter. And the flow they created a flow path that would go down through the center of the tube to keep the metal cold, and then come back up the outside to keep the hydride cool, and then they use that energy to drive the turbo machinery, or just put it right back into the reactor. So that was their assembly. They had the Zerk hydride and Inconel don't last at 2700 Kelvin, so you got to keep them cool. So you let the coldest gas go through that first, and then get it through the fuel elements. And then they just piece this whole thing together like a big puzzle piece into the reactor part there. They did some things at the end of the element because the hot hydrogen tended to erode a lot of the fuel. They came up with acceptable fuel loss and things like that, but they also tried to do things to protect that hottest end of the fuel element. So they did things where they could glue a molybdenum piece of hexagonal piece onto the edge of the graphite. So they came up with ways of brazing that on there, or brazing on a couple inches of just pure graphite onto the end of it to protect the end of the element against the hottest gases. So they were doing some pretty sophisticated high temperature materials development at the time, both with graphites and refractories. So this is a real mess of a curve, but it's the chamber temperature and the chamber pressure. It's the operating map of the reactor or the engine system. So the lowest left-hand corner is no pressure, low temperature, so I'm off. And then you work your way up to the red dot at full power. You can come up in different ways. You can come up with high ISP or highest chamber temperature first, get to your highest ISP, and then come across and raise your pressure. You'd raise pressure by changing the turbo machinery and changing the flow rate. And you change temperature by changing the drum position and adding more and more reactivity to make it hotter, such that, hey, the fuel wants to run hotter to balance that positive reactivity that was added by the control drum. So it just tends to run hotter to to naturally feed back a control point. So they use these maps, so the little dots were how they did their test. They would come up. The real trick is the bottom left-hand corner, because you're not really all that controllable through there. So you try to move up through bootstrap up your way up to a point where I can actually control temperature and control pressure. So all these other lines are power lines, come up and down this way. So what megawatt rating of the core is, what all the power of the core is flow rate times the change in enthalpy from tank to chamber. So once you know your pressure and temperature of the chamber, you know the enthalpy of the gas, you know the tank enthalpy, and so it's just m dot delta H gives you the core power. So you create these power lines at different chamber conditions. Then the flow rate just goes up with the pressure and the temperature, so the density. And so they would use these maps to navigate themselves around and find the controllable points. So all the other limit lines are, what's my max temperature, what's my stall of the pump, what's my reactivity controllability. So you'd map out kind of like, well, what's my yellow band area? That's kind of like, I can operate anywhere in that yellow area, but I really prefer to stay within a green box for things. So you would then create a green box operating area for you to be operating within. And those are your safe zones, and you'd set up different set points to like pull yourself back in. But make sure you can traverse that line from the lower left-hand corner up to the upper right-hand corner in, say, 30 seconds. And we'll talk a little bit about what that means. All these other, the blue box there is kind of like the bootstrap, kind of like when you're pressure fed, maybe a little bit of a booster pump, and kind of spinning yourself up a little bit before you have a lot of heat. And that might be happening down at like a 5% power level, or maybe 25 megawatts instead of 500 megawatts. Now let's see, then all these other things are all limit lines. So you create all these limit lines for the turbo machinery, the pressure drop of the core, the max temperature of the fuel, control valve positions, how much controllability do you have on your control valve for the turbine, how much reactivity control do I have, can I shut the system down? Because hydrogen is a reactivity adder as well. They were doing things with the hydrogen to control reactivity, but if you had too much in there, the control drum's poisons could be rotated in fully and you'd still be critical. That's not a good thing if you want to shut the reactor down. There were a couple tests that they went through that too. They forgot to, they didn't forget. They didn't get the flow shut off soon enough. They had liquid hydrogen get into the core, the drums were rotated in, power puffed up very rapidly, got it hot, pushed out all the hot hydrogen, the reactor went subcritical again, They still didn't turn off the flow, went back up again. And so the reports reported those, and they had to figure that. The best thing is that they're so honest in the old reports, the well-documented reports. The paragraph for that describing that event said, hey, we've been doing all this work about the controllability, the stability of the system. The paragraph, next paragraph begins, and then the surprise happened. So, I mean, they're honest enough to say that in these great reports. Okay, so all the different operating modes to focus on the chamber temperature and chamber pressure. Everything ties to that, because those are the measurable things. Those are the things you control off of. And so there are early modes before you're like pre-chilling the piping to chill it down, and then bringing the reactor up to power, because you have to bring it up through very, very low power levels up to the point where it's actually adding significant heat. So you bring the reactor up, and that may take about a minute or so. All these things are happening before you're really flowing a lot of hydrogen through the system. And then finally you say, okay, now I'm ready to go. I'm in that little blue box at the bottom of my operating map. Come up through that kind of quickly, get myself all set to say, okay, now I'm really ready to thrust up. And so then you come up on that thrust profile, however you wanted to do that, and within 30 seconds go from 5% power up to full power. The nukes would say, geez, that's really, really fast. The rocket people say, God, that's so slow. So there's some other rules like that are interesting between the chemical rocket people and the nuclear folks with timings of different things we can talk about. Then you would hold for however long you want, and then you would come down on the same sorts of temperature and pressure profiles. So they'd be coming up at 150 degrees a second. Some of that was limited by, well, geez, the core is going to have to expand to do that. So there are mechanical limits on how fast you can heat up the system and how quickly you can transport that heat out of the solid fuel into the propellant. And then the same thing with the pressure rise. There are mechanical limits that are associated with the rate of pressurization and how quickly can you spool up the turbine to push that pressure through the system. But reactors, engines, chemical rockets, when you turn them off, they're off. Nuclear rockets don't turn off. The heat, there's leftover heat in the system from the fission products. And so you've got to manage that decay heat load until it decays it down enough to where it can just radiantly cool to the space. And so you've got to manage a cool down period. And they came up with different means of cooling the fuel where they, okay, well, we'll puff some hydrogen through, let the fuel heat up, and then puff some more hydrogen fuel to cool it down, and they keep the temperature within a band. Or they would come up with a means of doing that continuously. So when you've got significant heat loads, it decays off logarithmically, luckily. The first initial phases, you need to have active cooling, and then later on you can have more passive cooling or lower flow rates for that. And you try to match that. Nowadays with shorter burn times, because Nozzle was looking at like a total of endurance of like 10 hours or so, they would, now we have shorter burn times. That startup rate and shutdown rate have to be included into your estimates for the amount of propellant that you need and for the impact that it has on your effective ISP and effective thrust for that one particular burn. So these days people are doing a better job of it. Instead of just saying, well, that's about 3% hydrogen. Now they're actually factoring it into the mission profiles for that. So what is game-changing development doing? What's different for them is they said, hey, we want to use low-enriched fuel. Instead of high-enriched fuel, we want to use low-enriched fuel. What that means, commercial power plants use about natural uranium has about 0.7% U-235 in the uranium. The rest of it's pretty much U-238. People enrich it up to 5% for commercial power plants. People enrich it further for other purposes, for historical thermal propulsion units, for space reactors, and for other things that rapidly expand their energy. And so people want to use lower enriched fuel. And so what they kind of target is a proliferation safe number is as long as you're less than 20% enriched, so 20% of the uranium is U-235, 80% is U-238. And that's the mixture of the kind of like the threshold that they're having us look at right now. What that means is though, geez, the NERVA engines, 95% of it was U-235. So I could very efficiently pack in that fuel with a lower loading density of uranium keep like a 3 volume fraction of uranium in that zirconium carbide matrix and have high temperature capability and get the loadings needed to make a critical reactor. Well, now I've got 5 times more uranium loading in order to get the same U-235 loading in the same space. That takes 5 times more volume. And that's the big challenge for us, is to be able to make that. And oh, by the way, U-238 is also a neutron poison. So remember those 1.5 neutrons that you need? Well, U-238 is taking a lot of them. So you have to do things to improve the goodness of the neutrons that are reaching the fuel. And so we'll talk a little bit about those challenges. You need more moderation. You have to slow the neutrons down. So what GCD wants us to do is establish a conceptual design for an NTP LEU engine in the thrust range of interest for a human to Mars mission. So 25,000 pound engine, cluster 3 of them together, have a 900 second ISP. Those are the sorts of parameters that they've established for it. And basing that off of past mission profiles, I think they used design reference architecture 5 that all the other people were using. So DRA 5 was used by the solar electric, the chemical, and the nuclear folks to figure out, okay, mission profiles for like a 2033 kind of mission time frame. And then, but also we were challenged to also build, test, design, build, and test some fuel elements. So what kind of fuel element could we imagine doing and prove the feasibility of that? And we were challenged to start with a refractory-based metal system. So go with the cermet fuel. We'll talk about why you want to go with cermet versus the ceramics, and then later maybe future ceramics. But they said, okay, LEU and use refractory metals. Well, refractory metals are also neutron poisons. And so we're challenged now that they're like tying our hands. So, okay, we'll use refractory metals, but use low enriched fuel. And so the grand challenge was, is it actually feasible to do that or not? So we spent the last couple of years looking into that, but also building and working with those materials that are really difficult to work with. And then figure out, well, can you actually scale that up from lab scale to production scale such that you could deliver an engine in X number of years from now. And then also look into the feasibility of this exhaust capture. We can't just shoot the rocket engines off into the atmosphere. We have to shoot them into something that will capture that energy. So now I have to capture 500 megawatts of energy of hydrogen into a capture system. And so then you've got to, it started off as liquid hydrogen, you pumped it through the reactor, it got it really, really hot, and then within a couple feet you've got to turn it back into water. So the grand challenge of creating an exhaust capture system was also being looked at as well as part of this program. So what we came up with kind of like design, build, test cycles, and we had working through game-changing development, looking at assess the feasibility, look at prior concepts from NTP. I'm a big believer in looking at archive history, because why reinvent the wheel, or why not learn what they already learned for the interactions of all these high pressure, high temperature systems, and develop a pathway to develop the technology readiness level, moving it from TRL 2 to 4 to 6 to ultimately flight readiness. And figure out, well, what sort of technology demonstration missions would you have? How do you develop that, mature the technology through a series of subcomponent tests and terrestrial-based tests to look at that. How much can you do subscale? How much do you have to do full scale? And then ultimately, if you come through the technology demonstration mission, then you get into the engineering development program to truly design and build the real flight systems. So developing that roadmap through the technologies to deliver it. GCD is in the first phase of it, and the GCD program is kind of coming to an end this year we're wrapping up some of our analysis and some of our early testing, both the engine and the reactor components, and coming through our feasibility assessment right now. Okay, so materials of choice. Like I said, chamber temperature can be related to the fuel temperatures. Fuel temperatures may be running 100 to 300 Kelvin hotter than the chamber temperature, because you've got to drive that heat from the fuel into the gas. And so this is a figure of merit. This doesn't really show up well at all. Of different fuel forms. So the coated UC graphite, which we saw early from the earliest NERVA days, had ISP capabilities of about 850, and they demonstrated that on some of the NERV engines. They got 800, 850 seconds out of some of them. But the coated UC graphite were limited to those low temperatures. The next ones were, okay, now let's go to that composite. Let's go to that composite matrix. We can push the temperatures up a little bit more, get a little bit more ISP out of it. After that, then you say, well, gosh, they're limited in what they can do with temperature. The next best thing is the refractory metals. So that's why they're looking at cermets and uranium oxide or uranium nitride cermets in a metal matrix. And you just pack particles of the fuel inside a matrix of metal, and you form that same looking engine. GE710 and Argon and ANL 200 were concepts that used the refractory metals. They tended to be fast reactors, and they could be fast, meaning that, okay, they use fast neutrons instead of slow neutrons to drive the criticality. They could be very small, compact, high power density, because the thermal conductivity of the metal was a heck of a lot better than the graphite. Then after that you push up into, then you say, well, let me go to the true carbides. So the Russians did an awful lot of work in uranium, zirconium, niobium carbide systems, and to push up to the highest temperature capability. So they were doing some tests of very small fuel thicknesses, twisted ribbon stuff. They did tests on these binary and ternary fuel forms. And the US looked at that with the SNTP program by a particle bed. So Jim Powell's particle bed reactor system would have just had the gas flow over the particles directly. Forget about the matrix, just float over the particles right off the bat, because then you can get the highest temperature gas temperatures out of that. And BWXT did some work on that back in the early 90s, where they did some critical tests, some hot tests with Brookhaven National Lab and a few other folks to work on that concept. Which brought in a lot of the infrastructure of the Department of Energy, because we tested it out at ACRR, we did some critical tests at Sandia. Brookhaven was involved because that's where Jim Powell was, and he was the father of the concept. The Russians, at the end of Glasnost, they said, hey, we should do some stuff. So they got the Russian scientists to come over with their power reactors, the Topaz reactors, some of the 33 that they have flying up there. They had the rocket people come over and talk about their technologies, because we didn't want it to go all somewhere else. So the United States did an awful lot of work with the Russians in the early days to kind of look at testing some of these things or getting access to that technology. Okay, so me being a nuclear engineer, it's all about physics. So the bottom curve is really the best one. Is like, so the refractory metals, what the bottom curve is, it's the neutron cross section for absorption. How worthy or how probable is it that it's going to suck up a neutron that won't get to the U-235? So tungsten is kind of the red middle line there. The effective fission cross section, which is the important thing to keep regenerating the neutrons, is the green line. And HALEU kind of has a lower number relative to U-235, lowered by a factor of 5, because you've got less U-235 in that metal form. So what we compete with for the refractory metals, the cermet cores from before, they were able to use tungsten and rhenium, because rhenium's nice. The materials people love rhenium because it makes it more fabricable, more weldable, more malleable, especially for these super hard refractory metals. But rhenium has the worst cross-section of any of them, and you can't enrich it out. There are 2 isotopes of rhenium, and they're both bad. So the nukes say, get rid of the rhenium. And so that was a challenge for the materials folks. Oh, geez, what are we going to do? And then we also said, hey, tungsten's not all that much better, so we really need to reduce the tungsten out of the core. To use low-enriched fuel, we had to get rid of the tungsten. So we said, hey, Argon looked at using moly in their core, so let's use molybdenum. It doesn't have the high temperature capability, so looking at where we can use molybdenum as much as we can, because rhenium is bad, tungsten is 10 times better, moly is 10 times better than tungsten. And so people now are looking at for these thermal systems and refractory metal-based systems using low-enriched fuel to go with a molybdenum, more of a molybdenum-based system. And the trick is also, fast reactors would operate up at the high end, so that the scale is incident energy decades of EV. So we saw that the neutrons come out at 200 MeV or thereabouts, or 2 MeV neutrons. So they're way over here, and everybody's cross section is about the same. So really, a fast reactor, the game is what's the volume fraction of structural material and fuel material. And you can play games with that up in the fast world because everybody's cross section is about the same. But the 235 fission, the green line, is usually always higher. Then you don't want to get involved with that mess in the middle. So what commercial light water reactors do, and CANDU reactors do, and SNAP did, is you slow the fast neutrons down, the 2 MeV neutrons, you slow them down as quickly as you can to the low energies. So you skip past all that mess because you don't, the uncertainty of what's going on in there, and just the magnitude of the cross sections is poison. So you want to go from high energy down to low energy as quickly as you can. The best thing to do is use hydrogen. So hydrogen is the gas, or zirc hydride moderator. So SNAP used a UZRH fuel form. One neutron has the same mass as a hydrogen atom. So just thinking like billiards, you can transfer all the energy in one knock-on to that hydrogen atom and slow the neutron down to thermal energies. So that's why people like to use hydrogen or zirc hydride for the moderator. It gets you past that as quickly as you can. Other moderators, it takes a couple more knock-ons. So beryllium is the next best, because that might take like 10 knock-ons. Graphite, which is why HTGRs are so big, maybe take 20 to 30 knock-ons to get you down there every time you're bouncing into that mess. So hydrogen is the best moderator to use for systems, making good neutrons that now my fission cross-section is 200, it's 100 times higher, 2 decades higher than it was when a fast neutron. So we need that high cross-section to compete better for the neutrons. And so we throw the neutrons down to thermal energies, get a cross-section for fission to keep the neutron chain reaction going at a 100 times higher cross-section than a fast reactor has. So that's the game that the nukes play. They want to play in this world of how do I get good neutrons for the fuel, but then make sure that I don't have too high a power density in the core. So now kind of going back to more of the history of kind of like the rover program, is they started off and the initial conception was like in 55 or thereabouts, thinking of, hey, let's do something with nuclear power. Everybody wanted to do something. People wanted to make train engines, they wanted to make airplane engines, and they wanted to make nuclear rockets, in addition to making all the other stuff. So they had all the weapons people that had a lot of great ideas, not really necessarily want to make a bunch of weapons. They say, hey, what else can we do with nuclear power? Eisenhower's Atoms for Peace program spawned off a lot of this stuff, even though some of this initial stuff was really looking at defense kind of things for the nuclear rockets. So they came up with these programs to build up experimental development, engineering development, and ultimately get into a flight system over the years. So this is their roadmap to develop the systems. The Kiwi program was the flightless bird, so all the Kiwi tests were never flight engines, they were just the flightless birds. Phoebus, I don't know exactly why they came up with the Phoebus name, but that Phoebus was that big 4,000 megawatt system. They were the monster thrust engines. The Pee-wee nuclear furnace programs was, geez, you know, it's really expensive making 2 cores a year and burning them for an hour or two. To just do fuel development. Let's do fuel development in a little test reactor, a nuclear furnace program, and they could test 1 or 2 elements in a test reactor without having to build an entire core that might have 1,500 fuel elements in it. So it was more economical for fuel, fewer fuel elements, so you could do more rapid fuel development. Now, once you knew that the reactor system was feasible, then you say, okay, well, how do I improve the fuel element itself to last longer? And then the NRX program was moving on and on and on to actually integrating the engine system with the reactor systems. And so that was their roadmap, and everything came to an end in 1972. A lot of things seemed to end in 1972. Okay, so some of the other things, like I was saying, they tested 20 engines. They designed, built, and tested 20 engines in the Nevada test area with various different attributes that they wanted to get to. How long could they run it? How many burns could they do with it? What sorts of temperatures did they get to? So the series of tests over the years, they were testing about 2 to 3 reactors a year. So they had 2 test stands out there. They built the final one for NRX, and then the nuclear furnace testing where they did the fuel development testing. But that shows the size of the engines for that. And that Phoebus 2 and the 5,000 megawatt, that's what it was rated for, but they only got it up to about 4,000 megawatts or so. So that shows the scale. But they set up a little rail system out of Los Alamos, out of Nevada test site to move the engines back and forth between the test stands, and they had a radioactive shielding for the cab, and so they could move it back and forth. But they had their own rail line out there that they set up, a couple miles of tracks. And so they'd move them, they'd move the test stands, and they essentially plug it into the breadboard hydrogen feed system. That wasn't the engine feed. Well, it wasn't all the engine turbo machinery. It was just pressure fed or turbo machinery fed to supply it to the engine, so they could plug in a bunch of different reactors into the same facility to drive the hydrogen into it or other gases into the system. And they would just plug it in there, perform the test, and then they'd let it sit for a couple of days to cool down, and then they'd bring it back to their disassembly facility and do post-test examinations of the elements to see how well did that core survive, how well did it do, did any of the fuel elements crack. So they had a huge infrastructure out there where they had an assembly building to bring in the non-radioactive material, assemble the engine, test stand, roll it over to the test stand, do the test, and then roll it back to the EMAT building, which was our RMAT building, which is the radioactive lab. Huge hot cells set up to be able to do this out there. That building now has been torn down, and the doors are torn down.
Do you have an idea of what they were costing per year?
I just saw a slide today from Bill Emmerich, because the total program was about $2 billion. I forget if it was then year dollars or today's dollars. But essentially, if you did 20 reactors, he calculated it was about $100 million a test for the total. I mean, and they had hundreds or thousands of engineers working on this program, in addition to the Apollo program and the other programs that were going on. Essentially, the entire space program was taking 4% of the GDP at that time frame. Which then, oh geez, the Vietnam War is starting to happen and all that other stuff. So there was a lot of other stuff going on. But at the time, they were spending close to 4% of the GDP on the space program, which we're not today. So this shows it again, kind of like the tests in the desert area there. The nukes also got to do cool stuff with their reactors to look at, well, gee, we don't know if this thing doesn't get into orbit when we launched it. Well, how can we bring it back down to Earth and not have a problem? So they said, well, why don't we just have it self-disperse itself up in the upper atmosphere? So how do we make that happen? Well, we'll just make it go prompt critical or add a heck of a lot of power, rise very rapidly, and self-disperse the core. Not a bomb, but a lot of energy going in pretty quickly. So they did a test, the Kiwi TNT, transient nuclear test. It wasn't with dynamite. They created a special configured core, and they did the test where they rotated the control drum very, very, very rapidly. They explicitly drove them out at like 1,300 degrees a second. Added prompt reactivity. The power went up exponentially within milliseconds or microsecond, milliseconds, and added all that energy to the core, and then it blew itself apart. They had high-speed cameras, and they had all sorts of other test stuff that they did for this. High-speed cameras, they had radiation monitors and things going around, and they took advantage of this sort of test. How much can we get out of this test? So this is a major test. But they have movies of it, and the best is like you listen to the engineers, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and then the thing goes, and you hear the scientists going, wow. It's like, so they just blowing stuff up. They would do that with the snap reactors. They'd throw a snap reactor, which was sodium cooled. They'd throw it into water and see what would happen to it. So they could do these experiments back in those days. That's the heyday of doing nuclear things. But they were also very careful. It's careful of blowing up the reactor. They said, hey, this way the wind is blowing the wrong way. We can't do the test today. It's got to be when the wind conditions are right, so that the Nevada test site can kind of contain most of it. And again, to do that, it was 0.1 grams of U-235 fission to cause that to happen. So it doesn't take an awful lot of fission to make it happen. E equals mc squared again, but you added enough megajoules to self-disperse the core. And so, so there are all sorts of movies. I think you can find most of them online for some of these tests. Some of them are boring. You just look at this rocket engine going for 10 minutes and you say, okay, well that's kind of boring to watch. But they did make all these movies, and they're great science movies with that. Good explanations and quarterly movies for the quarterly progress of the program. They were spending tons of money on documentation and both video and paper. In the end, they built this final test stand. Most of them were fired upwards. The last test engines were fired downwards, and then they could capture some of the exhaust for that and integrate the engine into this. But they also would put this shell around it to be some shielding to protect the test stand from the radiation fields that come out from gammas and neutrons. And so they would put these clamshells around it. They'd be water-cooled clamshells that they would move up towards the reactor to kind of shield the environment and this test stand from activation and people. They have the people pretty far away when they're doing these tests. But the last test stand, it was the XE Prime, and the XE Prime 2 is right now at Marshall Space Flight Center. Harold Garrish got it, moved to the Space Flight Center. It's unfueled, but they brought essentially that rocket engine. Oh, I have it right here. They have it at Marshall, so that's at Marshall right now, where they've got great statues of all the different engines at the Marshall site. But they have the XE Prime 2, the second engine that was going to be tested but never was. So Harold Garrish got a hold of it and got shipped back to Marshall, and so they can actually open up stuff and look at different pieces of it.
So that engine was never tested?
This was not tested, no.
This is the one that was on display out at the Space and Rocket Center for about 20 years, and they thought it was just a mock-up.
Aha, yeah. I think the Space and Rocket Center used to have a Snap 10 too, but then they brought that out to a conference, and then Rocketdyne or somebody else said, hey, wait a minute, that's ours, we're keeping it. So there was a big fight over that, because that was a full flight mock-up system without the fuel in it. But it had all the thermal electrics, everything was there. And one of the days, one of the engineers that was one of the test engineers on it, he just had people sitting on the floor, him going over all the parts of the Snap 10 reactor. It was an amazing experience to have him talk about everything that happened with it.
Do you know where the mock-up is actually at?
Which one? The Snap or this one?
No, of the Nerva engine.
It's right there at Marshall.
No.
Oh.
That's the actual test engine.
Oh, no, I don't.
There was a mock-up. They thought they had the mock-up, but
Okay.
it was actually the test engine.
Oh, okay.
The mock-up is sitting on the side of the road out at Jackass Flats.
Excellent.
As you're driving along there through Jackass Flats, they've got the facility where the reactor that was tested is actually entombed in concrete, and that mock-up is sitting out next to the road.
Okay. Out in the middle of the desert, if you can get it on site.
Yeah.
Okay, so let's see. Other parts are, this is where I have less experience into orbital missions and things like that, but talking about, I found this great map of how to get around the solar system, like a subway map. It was kind of cool. Sometimes when I look at the delta, it has the delta V requirements to go to places, and sometimes when I look at those, they don't quite match up with other mission profiles that I've seen, but approximately the sorts of delta V's you need to get to different spots in the solar system. So it's kind of cool, and you can find that, just Google search solar system subway map, and you can find it. But that goes into the mission planning. What sorts of delta V do you need? How much thrust do you need? What's the ISP, and how does the ISP help you with that? And so getting the nuclear engineers used to, hey, mass is kind of important for things, not just being able to launch it, but to get the best delta V from whatever ISP that you have. So having a high thrust to weight ratio is a good thing, although for nuclear engines it may not be always the best metric, because the engines will tend to be heavier because of their nuclear reactor, especially using low enriched fuel. and high density refractory metals.
It's like a Washington D.C. subway mount.
Yes, exactly. Yeah, it's kind of cool. And then playing with the equations. Well, how does it play into trip time? What sorts of delta V do you need to have a short transit time? And can a nuclear engine give it to you? And so playing with the rocket equations to figure out what's my delta mass, how much propellant am I going to need, but then also for the reactor engineers, what's my reactor power that I have to provide in this small volume, and how do I get that heat out of the fuel into the propellant? So these are all sorts of people do all these different mission studies, but in order for you to go faster and faster, you got to have a higher and higher delta V. And can you actually achieve those high delta V's with a vehicle that you can actually assemble up in space and push it there? So they've done all sorts of studies, so kind of like reference around that DRA-5, where they looked at solar electric, nuclear electric, chemical, and now the forces of evil are combining. Solar electric and chemical are kind of like coming up with a hybrid mission for things where they say, hey, we'll use SCP for the long coasting stuff to get the high size people. We use the chemical rocket to give us our first big thrust acceleration. So they're kind of combining forces today and looking at means of doing that, but also starting from really, really high orbits. So they're saying, hey, SpaceX or Blue Origin or whoever, you put us up in that, you spend the delta V to get us up to that high orbit, and then we'll just use a little bit more delta V to go. Whereas originally the nukes were faced with starting off in lower orbits, and we had to spend all that delta V on our engine. Well, then okay, so well, let's go apples to apples and push the nukes up to those same orbits and start from the same spot. Then that shortened our burn times and made things even more advantageous for what we can do with that capability. But still, the NTP, to get the shorter trip times, NTP is the way to go. But you do need the mass keeps going up. A lot of that's tied up with the propellant to get the delta M, to get the delta V. So other people keep looking at things. So why is NTP attractive? We can do both conjunction and opposition class, and don't really ask me what that means, because I'm not an orbital mechanics person. All I know is like the direction in which way you head to Mars, and how quickly it may take you there, or how much energy you need to do there, or how long you want to stay on Mars. Do you want to stay for a month, or do you want to stay in a year, and things. And so NTP allows you to have some more flexibility. We can reduce the trip times down to a total mission time for like 500 days instead of 3 years. Transit times to 120 days. Most of them now are looking like more like 160 days to get there for trans-Mars ejection. Let's see, reduce crew health benefits. Well, you're not spending a year traveling to Mars, so you cut down your dose or chance of solar flares by half. So you could reduce the dose by half by going quicker. We could also allow us to have robust architectures to allow us to abort the mission up to a month or out to 3 months into the mission. So the chemical people would say, well, we could abort too, but they're going to have to pre-stage some of their propellant in order to come back. The nukes can do it all and come back, and so they have better mission abort profiles for things. And so people are looking at that as a selling point as well, that we can turn around and come back sooner or longer into the mission if we needed to. Assuming that it wasn't your engine that was part of the problem that we needed to abort. But all engines have that problem. And then we can play with mass, so we could have more payload capability. For trade mass of the engine for mass of payloads. So this kind of shows some things from Aerojet Rocketdyne, one of the partners on the GCD program, looks at all these different sorts of mission things to come up with vehicle architectures and mission profiles, and looking in, well, when can we abort? How much pre-staging do we need to have? And so they're making these comparisons to be more fair, apples to apples, between all the technologies for things. And so this shows one example of sort of what point in time can they abort and come back to Earth with all the different orbits for the.
So why the significant difference in abort times? I'm a simple guy.
Yeah, well, the only thing I can think is the propellant needed to do it, and so the propellant needed to get yourself back, unless the chemical rocket people pre-stage it. they can't come back that often. They may, and that's about as deep as I can go on that. But you have to talk to Aerojet Rocketdyne to have them come and talk. I'm not going to talk about this, except for this kind of shows the conjunction class for long-stay missions and opposition class for short-stay. The direction, both of them still kind of take a long time for the whole mission. It's just a matter of how long you're spending on the planet versus how long you're spending coasting to get between the planets. Where did they want to cut? Well, this is kind of interesting because it kind of shows the masses that you need for a pure chemical system versus an NTP. A lot of it goes into, well, how many launches do I need to have to assemble this vehicle? So for the nukes, we're trying to keep it within 3 to 4 launches of SLS. Each launch is $1 billion, so you want to try to keep yourself within the propellant tank sizes and the mass sizes. So each tank might be like 40 tons of hydrogen that you're launching up there. And so if our mission requirements say, gee, you need 125, well, that's a whole other tank. So we always try to keep within the increments of the propellant tank sizes so that we can avoid having extra launches of all that equipment to ultimately assemble it, because it's going to take you years to assemble it if the launch profile is every 6 months. Now, if it's every month, then you can assemble that vehicle more quickly. But right now, some of the launch profiles are saying, no, once every 6 months we can do an SLS launch. Mm-hmm. So that's going to take 2 years to assemble this thing. So this thing's floating around up there, almost like you're building a space station in some ways.
Shuttle every 2 weeks, too.
Right, exactly. And SpaceX trying to do 2 in 1 day.
Well, initially, the space shuttle was supposed to launch every week.
Yep. So then this also shows some of in order to do an opposition class, the chemical rockets really just can't do it, but the nukes can do it with a little bit more mass to be able to do that. So that's where this really comes into play. The chemical systems can't do opposition class missions. Okay, so I think this is my second to last slide. So benefits of it, okay, we've kind of already talked about. We're using monopropellant. We try to keep the amount of propellant that we're using down by having high ISP and just using hydrogen and not a mix. We can perform both conjunction or opposition class missions. The ISP, if we can get the ISP up that high, can make it less sensitive to the mission parts. New arrangements and materials look like it might be feasible to do low enriched, but it's a challenge because you've got to have so much volume and you've got to have enough moderation to get good neutrons. So we're swapping fuel volume, power density, for moderation, which boosts up the power density of the fuel, so then we have to cool it. So there's this big trade-off between the nuclear performance, the thermal performance, and the mechanical performance to fit it in as engine mass and size that's feasible.
And low enriched is 6%?
We're pushing up to, the 20% is the threshold. So normally low enriched for like commercial power plants is 5% maximum. And so you try, and that's for shipping and criticality and licensing purposes. The commercial fleet's limited to 5%. The proliferation kind of number is a 20% number, and then there's things that go on with the efficiency and poisons and stuff. So people consider high assay LEU to be 20%. A lot of the more advanced reactors want to push enrichments up to 10%, 20% because they can get longer core lives without refueling by pushing up the enrichments. So it's the energy content. The more U-235 you have in a volume, the longer you can burn it, or the smaller you can make it. And let's see, all those other things. So we're looking for robustness, permissions, and reducing design uncertainties. And so we're kind of coming through that. And this cartoon is one of our latest CAD drawings. Worked through NASA's contract and joining the forces of Aerojet and BWXT to kind of come up with the arrangements supporting the project for NASA. So we're generating these sorts of CAD drawings of our concepts to doing a little bit more than just the paper studies that have been done in the past. We're actually trying to do more hardware, more CAD engineering to kind of assess where are the challenges, where are the weak points, to then develop the tech maturation going forward? What are the long poles in the tent? And then the final slide are the things that I've kind of learned between rocket engineers and nuclear engineers. Is like on startup to full thrust and full power in less than a minute. The rocket engineers say, hey, gosh, that's so slow. We're used to 3-second startups. And well, I don't know how we're going to ride through all these harmonics. We're spooling up the turbine and everything else like that. So they're worried about the harmonics on such a slow startup. We're going, oh my God, this is so fast to go from 0 power to full power in 30 seconds. Normally that's called a scram signal for a commercial power plant when you're starting up at a 5 to 10 decade a minute startup rate. So the challenge is, can your fuel actually take that amount of heat, and can I control the reactivity? There's a lot of negative feedback, inherent negative feedback in the system, but being able to start up that quickly is a big challenge. Commercial power plants start up, go from 0 power to 100% power in a day. So that's what normal Dukes think about as a day, not seconds. On full thrust to full power, burn times of 10 to 20 minutes, or total mission times of about an hour or less. The rocket engineers say, oh my God, that's so long, I hope our bearings and combustor hold up. They're used to like 5-minute burns or less. Now we're talking 15-minute burns, and can the turbo machinery actually last that long? So a lot of bearing work and things like that to say, can they actually last that long of a burn? We're going, oh my God, 10 minutes. It's like, that's nothing. An hour burn, that's 100 grams of fuel for us. So it's really, we spend an awful lot of effort piling in 150 kgs or 600 kgs of fuel into the system. We're only going to burn 100 grams of it. So burn times are real short for us. We're used to years of endurance on a core, not an hour. On temperature and pressure gradients across different structural regions, the rocket engineers say, oh my gosh, we're dealing with hundreds of K per centimeter or 1,000 psi across a centimeter. We've got a chamber operating up at 3,500 Kelvin and cryogenic temperatures on the other side across half a centimeter of a nozzle. Dukes, what's your problem? And we're going, oh my God, we've got hundreds of Kelvin per centimeter across fuel, across other regions, and pressures across different parts and within our reactor system. And we're used to dealing with safety factors of 2 or more and all this heavy component stuff. And when the rocket people say, you got to reduce mass, we're going, but we've got to deal with all these different stresses. And mechanically, how do we do that? Then the last one, which was the latest one, which was really shocking to me, is when we heat up, the coefficient of thermal expansion may grow our core by, say, a meter. It might grow 1.5% or so, 1.5 centimeters, which, oh gosh, that's a lot of growth you have to accommodate, because the reflector's not going to grow. It may shrink in because it's going to cool down. The core is going to get bigger at the hot end, and it's going to grow longitudinally. So we have to have space allowance for like 1 centimeter or 2 allowance for the cold as-built engine to get hot. And then will it creep and grow and then stay and then keep creeping and ratcheting? So we were, and then plus reactivity effects with the growth. So we're all, oh my gosh, we're worried about a couple centimeters. Then one of the SLS engineers said, whatever, we worry about 1 foot or 2 of tank shrinkage when we fill the tank with liquid hydrogen or oxygen. I'm going, wow, how can that be? It's a really, really big tank, and so % shrinkage of a really, really big tank is like 1 foot. So we got to worry about the solid rocket boosters clanging into the tank. Well, okay, I guess that is a bigger problem than me worried about centimeters. So, and I think with that, that's the end.
Sure. You'll take a few more questions?
A couple, sure. 5 minutes of questions.
Well, how about this? Are any of you guys looking at sizing this thing for SpaceX's Starship?
Yeah, I know there was a recent Nuclear Innovation Alliance report that came out with SpaceX. SpaceX thinking nobody was working in NTP or something, I don't know why. But we haven't had conversations with Musk or Bezos, because Bezos wants to go to the moon with some things, or have nuclear power on the moon. The parts of this are to fit within the fairings, so there are certain size limitations. So we've been looking at those sorts of, well, what are the fairing sizes of the different launch vehicles? Because you've got to be able to fit it on the thing to be able to get it up into space. But we haven't been talking with.
You think
Musk.
Bezos is more open architecture, more accommodating to ideas like this?
I can't comment on that. I don't know. Sorry. Okay. Yeah.
The pressures have to be the same at both ends of the reactor, right? Turbo pump has to pump high enough pressure to maintain flow out.
Yep. Each one. So the chamber pressure kind of sets the performance of the thrust, given a certain nozzle. But then you've got to push all that fluid through, and each one of those regions will have pressure drops. And so the turbo machinery has to be able to pump that up to a certain pressure. The rocket people say, oh, we go up to 6,000, 5,000 PSI out of our pumps. I go, really? But so when they're having pressures that might be like 2,000 or 3,000 PSI heading into the nozzle section and the other parts, they don't really have a problem with the pressures. We have a problem with the pressure differential. So gee, I've got 2,800 over here and I got 1,000 over here not a pressure vessel that's pushing out on a pressure vessel that's pushing in. So it's like thinking about pushing on a Coke can. We have to worry about what's the thickness of that vessel or that pressure boundary interface. How thick does that have to be so that it will hold up long enough to not creep in or not crumple? And so bigger thicknesses mean more mass. And that's where I would keep encouraging them, lower the chamber pressure, because it's all stacking up, and especially when it's an expander cycle that has a turbine pressure ratio of some number, 1.5, 2. So whatever is heading out of the turbine, right off the bat, you get a multiplier on the pressure. Not a pressure drop, it's the pressure ratio to do the work, to pump it. So Nerva engines didn't initially have that problem because they were just a bleed cycle. And so all the system pressures were more close together, and their chamber pressure was 450 pounds, not 1,000.
How does the mass or volume of the lowly enriched core compare with the Nerva?
Let's say Nerva needed about 150 kgs of U-235 to be critical in their volume, and they could have lower loading densities of the uranium. We're seeing about the same amount of U-235 to be critical, but we need 5 times as much uranium to fit in that same volume. And so there's a volume constraint right there, and that's a neutron poison. And then we have to have the right balance of the other materials, the structural materials, to provide that sort of loading capability. In addition to also thrown in some moderator, that Nerva had 6-to-1 fuel elements to moderator. We have more moderators to fuel. So the amount of volume we're taking up in our encircling diameter is more of moderator and less of fuel, even though we need more fuel volume to shove in 5 times as much uranium into the system. So that's the challenge of the huge balance of keeping everything confined, keeping the rocket people with our mass. So it's a matter of playing games with the densities and the loadings that need to be critical, but also thermally, because you got to have small ligament sizes for fuel to get the heat out, but then piling enough that you have a structural sound rocket engine. Yeah, way back. Yeah, sure.
I have 2 questions. The first one is William Emmerich. He talked about breaking down hydrogen molecules into individual atoms and getting an ISP boost.
Yep.
Is that something you're looking at?
You can do that more easily at lower pressures. So the dissociation of the hydrogen will happen at a certain temperature, given a certain pressure. And so we do get a little bit of a dissociation at the temperatures that we're at, but because we're at a higher pressure, it's tending to keep the hydrogen atoms together. The lower pressure you go, the lower the temperature it will take to cause that dissociation. So you can come up with an effective molecular weight of maybe 1.5 or something, which then helps your ISP. So that's what Bill was talking about, is how do we push ourselves into dissociation temperatures to get that extra boost of ISP.
Now, the other question is, have you looked at any alternatives like thorium for fuel?
Thorium isn't really a fissionable material. So it doesn't really work. Thorium is more used for breeding fuel to make U-233. Right, so you would want U-233 coming from the thorium cycle, but we're not burning long enough to breed in that material, and so you really can't go critical on thorium itself. It's not a fissionable material. You need U-235, U-233, or plutonium-239 as your fissionable materials. The others are fertile materials, so they can make that other stuff, but they're not fissioning, except for at fast energies. Then everything kind of fissions at fast energies. Yeah.
What happens if you can't do it with 20% enrichment?
Then we tell people go high enriched. It's a lot better for nuclear performance. but
Possible, but
yeah, that's the challenge is by taking a look at the low enriched systems, is it really feasible or not, and how much mass penalty do you have for the political benefit? And that debate rages on today. And every 10 years they seem to do these interagency white papers on high enriched versus low enriched. And what are the consequences and what are the pros and cons of doing it? And so they're doing that again now. And say, geez, all right, these systems are kind of massive. Gee, if you went to high enriched, you could have a much better performing system for operational performance, maybe not political performance for things. And also, it's just like the other thing too is like the security measures that you need to work with high enriched stuff is so costly, and then you'd have to set up all sorts of stuff at the test stand, at the launch pad and stuff. So all the security that goes along with it is pretty darn expensive. So you weigh that against the cost of having maybe a bigger engine or a more massive engine to say, hey, I can at least work with the material without all that security cost. So that's it's not just proliferation; it's actually the security cost of working with that kind of material. Yeah.
Everything you talked about tonight, fascinating stuff, but it was fission-based system.
Yeah.
There have recently been some interesting articles in the popular press and others about work going on at Lockheed Martin Skunk Works.
Fusion stuff with
Bessemer.
Bessemer.
Fusion reactions.
It's 50 years away. No.
Realizing that's probably Brand X that's talking about that, so we don't.
Yeah, they've been saying that for 50 years.
Exactly. Yeah.
But what do you nuclear guys think there may?
Fusion is even better.
Relative to propulsion.
The fusion aspect allows you to get away from a solid fuel form. So you could go to a gas core reactor, which a lot of people looked at in the past, to get your temperatures up even higher. Get rid of the solid. You're limited always if you have a solid fuel form. So now if you go to fusion, it's a different end of the game. Now you're not dealing with uranium and stuff. You're dealing with tritium and helium and the lower hydrogens. And so really almost you could say, well, maybe I can use my propellant as my fusion device for things. But you're still generating heat, which then needs to be transferred to whatever your propellant is. And I don't really know much about some of the fusion systems except for seeing some stuff that Cheng Diaz has been working on with Bessemer for things and looking at those sorts of systems. But that's about all I know about fusion systems. And I think, isn't University of Alabama, Huntsville working a little bit on some sort of a fusion propulsion system or plasma?
Yeah.
Okay.
He's working on a pulse fusion.
Yeah.
But it works similar to like the Z-pinch.
Okay.
Although some of the plans include using uranium as a fission trigger for the fusion material.
Okay.
Yeah, pulsed fission fusion is what it's called.
Okay.
Take a small pellet of uranium, coat it with lithium and some other fusion fuels, and stick it in the Z-pinch device, and it's compressed into criticality.
Okay.
By the Z-pinch.
All right. I don't really know anything about that. Way back there.
So in addition to fusion, some things they were looking at in the past were liquid core. These were still fission reactors, but it was liquid core and gas core. Obviously, you have a much harder containing problem. And how do you
Right, the gas core is like how do you contain that fissionable gas and not lose your fuel at the back end. But there was a lot of work on that. And then there's a Pratt & Whitney Lantern core that I think they had. It was either liquid or gas inside of quartz tubes, and then they transfer the heat from the quartz tubes out to the propellant. The liquid cores, I'd seen some old concepts like having like a kind of like a pebble bed kind of configuration to get some heat out of it. The liquid cores, you'd still need to be able to confine that with the flow field around it to transport the heat out of the liquid into it. So you still need some sort of containment vessel, unless you're just forming this blob of liquid. But then ultimately, well, what happens when you turn off the engine? What happens to that material? And that's the same problem that the gas cores would have. Is like, how do you get it started up and how do you shut it down? So solid cores or liquid cores may have a better capability of turning the engine off. I'll go there, and then one last one. Yes?
I was just going to comment that the old Pratt design was called the nuclear light bulb.
Oh, okay. Yes, the nuclear light bulb. Yes. Okay. Yes.
I've seen some papers on it.
That's it. It wasn't lantern. It was the light bulb. Yes. I'm sorry. Yep. Exactly. Yeah.
I recall that.
Oh, I'm sorry. It was, no, it's the other guy in the blue shirt. Then you can.
Yeah, the low enriched, is that the restart on the reactor? Does that change the day there on potential commissioning capability?
For restart?
So you've got the startup and shutdown cycle, and you've got the reactor poisoning as a result of the shutdown.
Yep.
Does the low enriched change that game at all?
Not really. What it does is the low enriched, with all the U-238 in there, when you get what works well for commercial power plants and other fissionable things, is the U-238, as it warms up, the cross sections kind of change to absorb more neutrons with the hotter they are, so it's a negative temperature coefficient. And so it's a safety feature that all reactors design into it, or it's just the way the physics work, is that as you get hotter, it adds negative reactivity to try to turn the power back down. So if you get hotter and hotter, it's going to drive, hey, no longer do I have one-for-one trade, I've got one going out and 0.9 coming in, so power's going to go down and drive the temperatures back down. So with the U2 having a higher fraction of U-238 in the system, the Nerva engines could play more with their hydrogen and temperatures because they didn't have such a large defect from going from room temperature up to really hot temperatures. Adding right now with low enriched, it adds an awful lot of negative reactivity. They like to talk in terms of dollars and cents of reactivity. Having that low enriched form, you might add $3 negative of reactivity going from cold to hot. That has to be made up by the hydrogen or the control drum rotations. High enriched systems have lower amounts of U-238 in it, so the amount of negative feedback might only be $1. So now I have to have $2 extra of drum worth to manage that temperature defect. That's the bigger impact of using low enriched fuel than any sort of fission product poisoning. That's always going to come in no matter what. The more you moderate it, the more worthy those fission products become. But because we're only burning for a very short time, the amount of fission products that actually build up really don't play in the game, especially when we've got such a high core loading of fuel. So I think I should stop because
Thank you very much for your fine talk here tonight. Very informative. So we'd like to, keep up with you in the future. Maybe see how this thing goes. Maybe in a year or two, have you back.
Hopefully.
You have some new developments. You were some of your other cohorts in this project here. And so thank you very much. Thank you everyone for coming.